Good morning. So yeah, I'm Mark Engelberg, and this is...
Hi, I'm Alex Engelberg.
And our talk today is solving problems with automata. So hopefully some of you have seen this kind of picture before. This is a standard picture of a finite automaton, which is another name for a finite state machine. There are a bunch of states indicated by circles. There are transitions indicated by arrows. There is a start state, and there are one or more accepting states, usually indicated by a double circle. The automaton, we say it accepts a sequence of transitions if that sequence of transitions leads you from the start state to one of the accepting states. So for example, in this automaton, it accepts the sequence 0, 1, 1, 0, because that leads you from start to the one accepting state in this automaton. Now, I used to be a computer game developer, and for many years, this is how I personally used finite state machines, as a way to design and code very simple game AI. So what you see here is a picture of a sentry in a game who is responding to different events by changing behavioral states, from attacking to patrolling. And I've lately actually been seeing very similar diagrams being used to design core.async processes, because this is just a great way to show how a process responds to incoming events and messages over a channel to change its state. Now, a few years ago, I became aware that there is a lot more you can do with finite state machines than just this, though. And once I realized that, I started noticing many, many different contexts where finite automata can come into play. So today, what I'd like to do is, well, the two of us are going to show some puzzles, because I'm a big believer in the educational value of puzzles. So we're going to show a few programming puzzles where automata give particularly elegant solutions to these programming puzzles. And our hope is that at the end of the talk, you'll come away from it with an expanded notion of what kinds of things you can do with automata and know how to do it in Clojure. So the first puzzle today is something called the maximal non-segment sum problem. So the idea is you have a sequence of integers, and you are trying to find the maximum sum you can get by adding up some numbers in this sequence, some subsequence of these numbers. The catch is these numbers can't all be in a contiguous block. We call a contiguous block subsequence a segment. So we're looking for ones that are not a segment. So here down at the bottom, we see some examples. We have the sequence of numbers, and these are some different combinations we might look at. The red numbers, you can see we can't do any singletons, for example, because a singleton counts as a segment. The empty subsequence doesn't count, because that would be considered a segment. So you need at least two numbers, and they have to have some kind of gap between them somewhere. In this particular example, the maximum sum you can achieve in this way would be 5 by adding up the numbers 4, 5, and negative 4.
4 and 5 are consecutive in the sequence.
But the three numbers together do not make a contiguous segment. So that's the key.
Also, just 5 would be a solution, right?
Well, that's a singleton, and so a number by itself is considered a segment. So that would not be a solution. Make sense? It's a little bit of a tricky concept, but we're looking for a subsequence that is not considered a segment. Now, when you're faced with a problem like this, it's often not obvious how to proceed. One of the best strategies is to just come up with any algorithm you can that's going to solve the problem, even just some kind of crazy brute force method. So this would be an outline of sort of a brute force approach that might work. We need to generate all of the non-segment subsequences, sum them all up, and take the maximum, right? That's pretty much the definition of the problem. It's not entirely obvious, though, how we write this all non-segment subsequences function. Now, there's a couple insights that can get us in the right direction, though. The first insight is that every subsequence can be expressed with a bitmask of zeros and ones. So here we see, like in the first example, we're selecting -1 and 5 out of the sequence, so we put 1s in those positions. It's very easy to implement a closure function that takes a bit mask and a sequence and extracts out the subsequence. Now the catch becomes, how can we recognize from these bit masks whether it is a segment subsequence or a non-segment subsequence? There's a few ways we can do this, but the way that leads us in the most interesting direction here is to think about the fact that the sequences that form non-segment bit masks can be described with a regular expression. So in this case, we're saying we start off with a bunch of zeros, perhaps, which is the things we're not selecting. And then at some point, we have to start selecting some numbers. We get a run of 1s. But then at some point, we need that gap. So we're going to have to stop picking things. That's a run of zeros. And then at some point, we need to pick something again. And once we've done that, we have picked some things that have a gap between them, and from now on, we can pick either 0 or 1 for a bit mask. So this would be a regular expression that describes a non-segment bit mask. Now, the next key point about this is that every regular expression has a corresponding finite state machine, a corresponding automaton. This is one of the big results of automata theory, is that there's this correspondence. The other cool thing is that Zach Tillman wrote a library called Automat that makes it really easy to build such a state machine. So in this case, what we're doing, we could maybe try to use the built-in regular expression machinery, but we want to do this kind of regular expression pattern matching on a sequence of numbers. And so this is the natural way to do it with this Automat library. So what's going on here is you see, this is basically infix notation for the regular expression. I mean, not infix, the opposite, prefix notation for the regular expression, and then you do compile at the end, and that builds the finite state machine. So it's a very useful library. Now there's a couple other interesting things you can do with the Automat library. One is you can visualize these automata that you've built with this view function in the viz namespace, and this is the picture you see up at the top. And you can see this is doing exactly what we expect. We can have a bunch of 0 transitions, and then we eventually need a 1 transition. We can have some more 1s. We eventually need another 0, and eventually another 1. And then at that point, it doesn't matter what we do. The other really key function in the Automat core namespace is this function advance. We're used to thinking of automata as these very stateful entities, but the Automat library embraces the closure view of these things as immutable data. So advance is a function that takes an automaton, and it takes the current state of the automaton, which is some kind of immutable object, and it returns a new state, so a completely different object representing the new state. So that means that we can advance through we can sort of step through all the processes of an automaton by taking the output from one and just feeding it right into the next function. At the very beginning, we don't necessarily have a state to feed it, and at the very beginning, you can feed in the Automat library, you can feed it an initial value that kind of gets stored and passed around, and that lets you do some interesting things. You can design your automata to update the value in interesting ways as you progress. But in this particular example, we're not really using that, so I just pass a nil at the beginning, and nil just gets threaded through as a value. But what's really interesting here is the way you keep sort of passing in the return state to the next call of the function to step through it. Once you have this advance function, it's not hard at all to write this non-segment bitmask predicate function. Basically, we just kind of do a reduction on the sequence by keep stepping through the automaton with each of the numbers as the next transition. And at the end, we look to see if it's in an accepted state or not. At this point, we have the tools we need to build that all non-segment subsequences function. So what I've done here is I've used from the math.combinatorics library, the Cartesian product function, which lets us build a sequence of all of the zeros and ones of the right length as the original sequence. And then we filter, I need to drink water for a second. We need to filter on this non-segment bitmask. And then we do that apply bitmask function to extract out all the sequences. Okay. So now that initial brute force strategy, it would actually work. We've implemented all non-segment subsequences. So this thing would work just fine. Very slow though, right? It's O of 2 to the n. I mean, because at some point you got to generate all the 0 and 1 combinations for the length of the sequence. So the question is, can we do better? And the answer is yes. The first observation that kind of gets us in the direction of doing this quicker is that right now we are first generating all these subsequences. We're making all the passes through, and then at the end we're summing it all up. And so the first question we might ask is, can we do both of those processes in one pass? And the answer is yes, we can. So if we have a sequence in the bitmask, we can both check whether this is a non-segment subsequence and find the sum all in one pass pretty straightforwardly. We start off knowing we're in state Q0 and with a sum of 0. And when we see a 0 in the bitmask, we update the state, but we don't update the sum. When we see a 1, we update the state based on the transition diagram, and we also update the sum. And we just keep moving through the sequence like this. And at the very end, we see we're in state Q3, which means we're in the accepting state. We did find that this was a non-segment subsequence, and we know what the sum was. Okay, well, how does that help us? It helps us because there's this really cool thing we can do, which is to analyze all possible subsequences and do the sum, or find the maximum sum, all at the same time in one pass. And here's how it works. We start off, again, knowing that we're in state Q0 with a sum of 0. Now for this first number, as we're making one pass through the sequence, what we do is we consider both possibilities for the bitmask. It could be 0 or 1. If it were the 0, we would end up in state Q0 with a sum of 0. And if it were 1, we'd end up in state Q1 with a sum of -1. Make sense? Now, for the next step, again, for each of the two possibilities we found before, we're going to branch out and look at what would happen if we did the 0 transition, what would happen if we did the 1 transition. So again, we get a bunch of states and sums. But look here, we have a duplicate for Q1. And we only care about finding the maximum. So this Q13 is irrelevant. It's already dominated by this Q14 possibility. So we can just collapse it down to this. Again, for the next one, for every state and sum we have, we look at the different possibilities. What if we saw 0? What if we saw 1 next in the bitmask with this particular number in the sequence? So we're either going to add in the 5 if it's a 1 transition or not if it's 0. And again, we get all these possibilities, and we get some duplicates, and again, we eliminate the ones that aren't the maximum. So this allows us to keep going down all the way to the end. Each time, we do sort of an expansion and then a collapse. And then at the very end, state Q3 is the only accepting state. So only the sequences that landed us in state Q3 are the ones that were the non-segments. And so this is the maximum sum you can get, 5. That's our answer right there. So that's how you can do this with one pass. And here's what the code looks like in Clojure. One of the things I did here, just to sort of demonstrate how you would do this in Clojure, is I took the transition information and embedded it right in the code right here. So this is a great way, if you already know the transitions and you don't need a library like Automat, you can just encode this directly in Clojure as a map. So we have a map that says, from state Q0, if I see 0, I go to Q0, and if I see 1, I go to Q1. So this is just a straightforward representation of that transition diagram. And then this reduction is exactly the algorithm I described. At each part, we look at what happens if the transition is 0 or 1. We either add to the sum if it's 1 or not if it's 0. And we're using max to kind of merge all this together at each step. And then at the very end, we look at what's in Q3. So this is exactly the algorithm I described. Now, interestingly, you can generalize this, right? Because this process works with any kind of subsequence where we can describe that bitmask by a regular expression. So let's generalize this to a function called maximum sum that takes the regular expression that we're looking for the bitmask and the sequence. So this is the problem we just discussed, because this is going to be how the non-segment regex, so this is the maximal non-segment sum. Well, some of you may have seen there's a fairly popular interview problem is to find the maximum segment sum, which is actually considerably easier than this problem. But this general purpose function can do both of them. You just plug in a different regular expression. Or we could do something totally crazy like the maximum length where we're extracting segments of exactly length 3 or something like that. As long as we can describe it with a regular expression, this algorithm can do it in O of n time, 1 pass. We could even step it up a little bit and have it show us both the sum and the bitmask that it used to find it. Now, I've included all this code for the generalized functions on the GitHub site, and also showed another example with an alternative automata library for Clojure called reduce-fsm. And these are, so you can look there for more. We have a lot more we want to cover, but hopefully this gives you a sense of some of the power of what you can do. Basically what's going on in the algorithm, if you look at the website, is I'm using instaparse to pull apart that regular expression string, and then I use the automat library to rebuild the actual automata and then the automaton and then extract the state transitions out of it to do the exact algorithm that I did before. So the big ideas from what I've discussed so far is that the automat library is a very powerful tool for working with automata. It's especially useful if you have in your head like some sort of regular expression style description of what you want to match against. And you want to build a finite state machine. It does that for you. And the other big ideas here that pretty much any time you see something that looks like a regex, you should be thinking of finite state machines. And for best performance, as we saw in this particular problem, you ideally want to interleave that process of constraint checking with your computation. Now, these last 2 points, thinking of finite state machines as constraints and interleaving constraint checking with computation, this might make you think of there's a whole branch of programming called constraint programming. And that's pretty much what that is all about, is doing constraints and interleaving the constraints with computation. Now, Alex wrote a library for Clojure called Loco, which makes it very easy to do constraint programming from within Clojure. So next, he's going to talk a bit about how automata fit into the Loco library.
Okay. So I first discovered constraint programming. So first, how many people here have heard of that term, constraint programming? Okay, cool. So it sounds like a lot of you have at least heard that. So I first heard about constraint programming in a online discrete optimization course, and I was really fascinated by that concept. So I think like a couple of years ago, I created a library called Loco in Clojure, which is basically just a kind of a Clojure-friendly front end to a Java library. It's a pretty cool, robust constraint programming library called Choco, which you can also go check out. In this talk, so first, for those of you who haven't even heard of constraint programming or those who aren't really familiar with what it is, I'm going to give you sort of a whirlwind tour of what that is, just so we're all on the same page. Then I'll show you how we can sort of combine that with automata. So the way Loco works is it works with finite domain integer variables. So basically, any integer variable that has a concrete minimum and maximum bound, or some set of values it could be. So here we have a pretty simple problem where we have variables x, y, and z. They're integers, and they're in a finite domain, 1 to 10,000. And we have one constraint, which is x plus y plus z equals 5. So this is a pretty simple program to just do manually brute force. So here's just a quick brute force solution. The problem is that this is super slow, mostly because of my excessive domain size that really slows it down. So I'll show you how to do that in Loco. And in a second, I'll sort of explain to you kind of the secret behind why this is faster than brute force. But first, I'll kind of go through the syntax of how I'm expressing this in Loco. So here, I'm creating a constraint model, which is a vector or a sequence of constraints that I've constructed in a Loco namespace. Here I'm saying x, y, and z are in 1 to 10,000. And I have my constraint here, which is just kind of elegant prefix notation that we all know and like. And I have this model, and I can pass it to a function called solutions, which it just kind of consumes that constraint structure and then gives you all the solutions. Or if I wanted one solution, I just say solution singular, and that would also work. So if I do this at the REPL, then first of all, it completes, which is nice. And also it gives you a sequence of maps, and for each map, it gives you x, y, z. So here we have 6 possible solutions where x, y, and z add up to 5. So what is the secret behind this? So the secret is a little thing called propagators. So in Loco, every time you give it a constraint, it's telling it to make a propagator for that. So a propagator's job is to efficiently remove from each variable's domain all the impossible values based on the constraint that I gave it. And so essentially what a propagation engine does is it's sort of, if you imagine like a depth-first search, but every time you go into the search tree or make some kind of decision, then before you do that, you run all of your propagators to trim all the domains first. So here's sort of an example of that. So here's our propagator model. We have the domains, and then we have one propagator. So step 1 is to run all the propagators and see what happens. So here we can deduce that x, y, and z cannot be 4 or more. Just that makes total sense because even if x were 4, then even at the minimum values 1 and 1 for y and z, then that would already add up to more than 5. So we can just deduce right off the bat that x, y, and z cannot be 4 or more. So we're just going to trim that domain right then and there. Then we sort of start our search and then make a decision and sort of guess that x equals 1 and see what happens from there. So here we go back to the propagator step, and then there's no more deductions we can make. So we're going to make another random stab in the dark and say y equals 1, and then see what happens. So our propagator kicks in again and says z equals 3. So now we have a solution. So that very quickly honed in on one possible solution. And then after that, if we want to continue finding solutions, we would backtrack and say, okay, remember that time when I said y equals 1? Now y is not 1. Now let's see what happens. So I'm not going to show the rest of the search, but that's basically the gist of propagators. So just to give you a taste of what kind of constraints you might find in a constraint engine, these are all things you can use in a constraint model, and they all have their own propagation algorithms that do this. So we have equality, inequality, logical meta constraints, which is kind of cool, and or not. We have just some more math stuff, min, max, abs, all that stuff. And then we have global constraints, which is sort of more advanced properties on a list of variables. So here, for example, we have distinct, which is like all these values must be all different. One more thing before we dive in, sort of just a little Loco trick I want to mention so you understand the code a little better. In a constraint problem, then you'll a lot of times have situations where you have a list of variables or a matrix of variables. And in math notation, we would just use a subscript for that, where we have like x sub I for all I in some range. So I just want to say the way to do that in Loco is I'm just having a vector of the keyword x and a number, and I'm passing that to the in constraint and just generating a bunch of constraints and a for loop and then concatenating those lists together to create my constraint model. So that's pretty simple. So now it's time for fusion. So that's the first and last meme I will use in this talk. You're welcome. So what if we could combine the flexibility of regular expressions with the efficiency and power that we just saw with propagators? So the answer is a little thing called the regular constraint. And it's a constraint that actually has the name regular, so it sounds really kind of boring and stupid, but that's actually the name of the constraint. So here we can sort of create an automaton and constrain that a sequence of variables must satisfy the automaton. So as he was saying, sort of the way you satisfy an automaton is you pass it through the transitions and see if it gets to a final state. And so we can create an automaton. As he also said, you can turn a regular expression into an automaton. Loco has a function that just lets you easily do that, and it says it's just called string to automaton. It'll generate like a automaton object you can use in the constraint. So I have this regular expression, and I'm passing it to this regular constraint. And if I were to solve this, then there's actually only two solutions for this. If you look at the regular expression and also consider the fact that the C variable must be 3. So this is a propagator that's surprisingly powerful in constrained models. Also, I want to mention the regular expression is a cool way to construct automata, but if you can't think of a regular expression to express something, you can also just write out the transition table yourself. It's the same syntax we were seeing in part 1. You also have to specify the start state and also the set of all the accepting states. So with that, code. So one of sort of the killer apps for constraint programming that most people use it for is something called scheduling. There's like job scheduling, workshop scheduling, warehouse scheduling, all that stuff. And constraint programming is really good for that. So I'm going to do a variation on that called nurse scheduling. So the problem is we have 7 nurses in, I guess, a hospital, and there's 10 different days. We want to schedule all those nurses' shifts for the next 10 days. So as you can see from this sort of example solution, then we can, there's 7 nurses, 10 days, and in each cell is sort of what kind of shift they have on that day. So we can give a nurse a day shift or a night shift or no shift on that day. So constraint number 1 is there must be 3 nurses covering a day shift and 2 nurses covering the night shift on any given day. So if you just pick something random like D7, then we see 2 N's and 3 D's. So that constraint is satisfied. So that right there is sort of like a normal scheduling problem. And then now we're going to add a couple more constraints that sort of are a twist that require a regular constraint. So constraint number 2 is that a nurse can't work on more than 3 dates in a row. I'm saying date so it doesn't sound like day, because day and night shift are different things. But a nurse can't work more than 3 dates in a row. So that's satisfied in this table. You can see that you see like chunks of 3 at most, because after 3 days, then they need a rest, I guess. Lazy nurses. So the final constraint is sort of on top of that, a nurse also cannot work 3 nights in a row. So all that really means here is that in these chunks of 3, you're not going to see 3 N's specifically. So those are the 3 constraints we have to work with. So what are the variables we're going to use in this constraint? So I'm going to have a shift ij, using that sort of subscript notation I was talking about, where it's sort of what kind of shift the nurse number I does on day number j. And Loco only works with integers. So if we have something like kind of like an enum kind of thing with day, night, or nothing, we have to map that to a set of integers to use. So we have day is 1, night is 2, nothing is 0. I just kind of picked those arbitrarily. So there's 70 variables we're working with. And so constraint number 1 is pretty straightforward. I'm not going to go into the details, but I'm using a cardinality constraint, which is just a really simple way of saying there's this many of this number, there's this many of that number in a series of variables. So we're just going to run that constraint on all the columns. So I'm not going to go into depth on that, but that's covered. So now constraint 2 and 3 is where it gets more complicated. So what I'm going to do here is I've written an automaton, or well, I haven't written it, but there's an automaton that can parse a sequence of shifts and then sort of validate whether that sequence of shifts for a given nurse is okay based on the constraints I just outlined. So this is the transition table. You can't really see at a glance exactly what it's doing, so I've written just a quick like rhizome code. So here's the diagram for that. So right off the bat, you can see something kind of interesting, which is that all of these states are accepting states. They have that double circle on them. And so what that means is that the way that this automaton passes an input is if if the input can go through all the transitions and not hit a node where there isn't a transition coming out of that. Because as you can see, there are certain nodes here, like Q6, for instance, where if you get here, you can only pass it in O to get back to the start, and there is no N or D arrow coming out of here. So if you were to pass it D, 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 then now you have to not have D or N because the nurse needs a break. So that's basically the gist of this automaton. For example, if you were to say if you were to say N, N, and then you're only allowed to do D or a break. So does that automaton kind of roughly make sense? So I've created this automaton called shift automaton because it's parsing all the shifts. And then I'm just going to use a regular constraint here and use that on all of the different rows for each row of nurses. So let's see how we did. So it only takes like a second or so, but boom, we have the nurse schedule. So that was sort of the first puzzle. I think I have time for another one.
Yeah.
So, okay. So one more puzzle for you. So this is sort of a practical example of what people actually use constraint programming for. I don't do that. I am a recreational constraint programming user, and I like to sort of use Loco to solve like kind of actual fun puzzle things. So
Make the font bigger.
yeah, I will embiggen this. So here's the problem. We have a crossword puzzle, kind of. It's actually just a 5x5 grid, but we want to fill it with letters such that each row or column is a valid word. So that's pretty simple. So what are our variables going to be? So again, we have a grid. So we're just going to say cell ij, and I is the row, j is the column. Pretty simple. And again, we can only work with integers, so we have to somehow map characters to integers. That's really easy. We just kind of get the ASCII code of the character, because why not? So the domain is 97, which is A, to 122, which is Z. So there we go. So that's the variables. Now we have to figure out how to constrain the word piece of it. I have a dictionary of the 2,000 most common 5-letter words, courtesy of Knuth. And so here's sort of a slow potential approach to this word constraint. And sort of if you didn't have the regular constraint available to you, what could you do? So the answer is perhaps something like this, where you have a giant or statement, and for each case, you say, okay, it could be this word, or it could be this word, or it could be this word. That's really slow, but that's kind of the gist if you were to do that. And the constraint engine doesn't even finish if I were to just use that awful, terrible constraint in place of a better one. So the fast approach is to use an automaton. So here is the transition table of an automaton that I've created for this. And you could actually probably figure out what it's doing from here, but I made a diagram for you anyway. So here, I'm just assuming we have 3 words in the dictionary, dog, cat, and duck. So let's just see how that works. So you have a start state, and it's pretty simple. If you say DOG, you get to this final state. Each state is sort of how many letters you've correctly consumed so far. And then the final states, of course, are the complete words. So I assume that makes sense to everybody, this dictionary automaton. And So I'll just create a dictionary automaton from the dictionary that I have, and that ends up with like several thousand states or so, which is not really a big deal. So let's see how this works. Okay, cool. That was easy. This is easy. Let's make it harder. So here's the more complex example. So I give you the 5x5 so you can get your head around the constraints involved and all that stuff. I'm not going to go into any of the actual code for this, but this is just like kind of a more intense example where I have a more legit looking crossword grid. And so it's sort of like solving an actual crossword puzzle you find in a newspaper, except there's no like word clues or anything. It's just, so the hard part's out of the way, and we just have to fill it in with a bunch of letters. So I'm going to use the exact same automaton and the exact same variables and all that stuff. It just, I'm using it on sort of each chunk instead of the entire row or column. So I think that's all you really need to know about this to get your head around what I'm doing in this. The code is on GitHub if you want to see. So this takes a little longer. This is going to take maybe, so it takes some time to just generate the automaton, because I'm using a different dictionary. Instead of the Knuth 5-letter word one, because I want all the different lengths, I'm using a very, very large word dictionary for all of the different sizes of words. And so it generates a giant automaton, which is 6.8 seconds, and then 7.6 seconds to actually solve the model. So these are all valid words, asterisk, where, because the dictionary is like, has really obscure words in it, so it's not going to be like, yeah, whatever. Just like a real crossword. So that's that's pretty much the extent of my code demo. You've seen two examples. There's the kind of like what people actually use constraint programming for, and then what I use constraint programming for. Okay, so big ideas for part two. So as I mentioned, propagators are super powerful. They can really easily pinpoint a solution in a vast space of solutions. The regular propagator in particular is really cool because all we have to do is give it an automaton or a regular expression, and it can do this cool propagator party trick. And then I guess the last takeaway is if you want to try this for yourself, you can go check out my Loco library, which has support for constraint programming, integer, finite domains, and also the regular constraint. So that's it, and we have like a couple minutes for questions.